Hello everyone, and welcome. In this demo, we're going to explore the fascinating world of 3D transformations by animating a Helix Spring using Python and Matplotlib.
Today, we'll break down the fundamental transformations, the translation, rotation, and scaling, and see how they are applied using matrix operations. We'll be using NumPy and Matplotlib along with MPL toolkits that Mplot 3D to visualize our helix and its transformation.
Before we dive into animation, let's take a look at the basic helix we'll be working with.
This is the basic helix we'll be transforming. Now, let's walk through the code that makes this possible.
First, we import the necessary libraries, NumPy for numerical operations, matplotlib.pyplot for plotting, mpl_toolkits.mplot3d for 3D plotting capabilities, matplotlib.animation for creating animations, and matplotlib.colors for color manipulation.
Then, we define the several parameters that control the appearance and behavior of the helix and the animation, such as the number of coils, radius, base height, animation speed, colors, and the number of frames for each animation phases.
These parameters allow us to easily customize the animation. To generate _helix points, function is responsible for creating the 3D coordinates of the helix. It uses parametric equations,
where t is a parameter ranging from 0 to 1. This function generates a set of x, y, z coordinates that define the shape of the helix. That np.lenSpace is used to create evenly spaced values for t, ensuring a smooth helix. The color_helix_points function assign colors to the points of the helix, creating a gradient effect. It iterates through the points and assigns colors based on their position along the helix using the color_cycle list.
This function using matplotlib.colors to blend between the colors in the color_cycle, creating a smooth color transition along the helix.
Now, let's move on to the core of the animation, the transformation matrices. These matrices are used to perform translation, rotation, and scaling of the helix spring. We'll define functions to create each type of transformation matrix.
The create_translation_matrix function creates a 4x4 translation matrix,
where tx, ty, and tz are the translation distances along the x, y, and z axes, respectively. This matrix shifts the object's position and 3D space.
The create_rotation_matrix_z function creates a 4x4 rotation matrix for rotation around the z-axis,
where angle is the rotation angle and radians. This matrix rotates the object around the z-axis.
The create_scaling_matrix function creates a 4x4 scaling matrix.
Sx, Sy, and Sz are the scaling factors along the x, y, and z axis, respectively. This matrix changes the size of the object.
Y_transformation_matrix function applies a given transformation matrix to helix points. It first converts the 3D points to homogeneous coordinates by adding a 1 as the fourth coordinate.
Then, it multiplies the homogeneous coordinates by the transformation matrix. Finally, it converts the transformed homogeneous coordinates back to the 3D coordinates.
The fun part, the animation. The animate function is workhorse here. It's called repeatedly by Matplotlib to update the plot for each frame of the animation.
Animation is divided into several phases. It starts with the original helix, which is displayed for a few frames without any transformations.
We introduce translation. Notice how the helix moves along the y and z axes. We're using sine and cosine function to create a smooth oscillating motion.
Now, we rotate the helix around the z-axis. The rotation angle increases linearly with the frame number.
After rotation, we scale the helix along the z-axis again. The scaling factor varies sinusoidally, causing the helix to stretch and compress.
Now, for the grand finale, we combine all the transformations, translation, rotation, and scaling. This is where things get interesting. Mathematically, this is represented by the matrix multiplication, transition underscore matrix, at rotation underscore matrix, at scaling underscore matrix.
Finally, the helix settles into its final transformed state, showcasing the cumulative effect of all transformations. So, to recap, we've seen how to generate a 3D helix and apply various transformations using matrix operation in Python and Matplotlib.